Tak. Czekaj, już. Tylko Marek, chodź szybko.
Jak są takie małe...
Jedno zdanie. Panowie? Dobra. Alright. Jesteśmy? Mikołaj? Alright, guys. I think we're alright right now with the link, so sorry for the interruptions, sorry for the technical problem, but it's definitely not up to us here. It was an external problem, but we fixed it. I think we are live again, so thank you very much for your patience. Yeah. That will help a lot. Thanks a lot. Well, that proves again the great community of Berlin enthusiasts of decentralized technology, of Ethereum, of Golem. So thank you very much. Julian, I know that you'd like to present this shorter version of our recent.
No. I think the best idea is that because we are going to upload everything anyway. So if you lost anything due to streaming problems, you're welcome to see that part later on once we upload that. I believe that this proves that we are very much focused in Golem now on the visual part, which is rendering. We haven't come to sound yet or to live streaming yet in Golem. Hopefully we'll have any more problems with that. Please confirm on Slack that we have no problems. I'm going right to my computer to check if you confirm on Slack that you can hear me now. And Alexandra and Piotr, please continue from where you ended. Sorry, guys, once again for the problems, and sorry all of you here for waiting, but I think we enjoyed this little unplanned break. Thank you.
Yeah, guys, so to you, just thank you once again for being so patient. And just let me address our great community watching us there right now. We really care about you being there, so that's why we had to take this technical break. I think it was very important. I know now that the sound is great, so I hope I could hear you as well and your feedback, but right now this is the most important thing, so you could hear us. We are...
Slack is asking to make it louder.
Okay, if the Slack is asking to make it louder, your wish, Slack, is our command. So let's make it louder.
Okay, so for all of you that missed the first part of the talk, how to implement NAT traversal on Golem, and I was talking how to implement neural network training on Golem, and that you can distribute it, not full neural network training, but hyperparameter tuning. Okay, so let's leave this distribution behind and talk about verification. As it was mentioned before, it's a sequential algorithm. So each block on this picture represents one iteration. And we want to use exactly the same framework that was used for RAS rendering and for net traversal. Local verification, probabilistic local verification. So you want to check small part of the computation. And by small part, in this case, we understand single iterations. More iteration you check, the higher probability is that the full data is correct. So provider pre-commits the hashes of the state after each iteration to requester. Then requester asks him about some random iteration. And provider is supposed to send the full state. Requester repeats this single step and check if it's correct, and it hashes to this pre-committed hashes that was sent before. If we additionally somehow randomize these input data that are there, for example, by doing some permutation of batches or different subset of batches that are known to both sides, we can be sure that there are no cycles in this data. Yeah, that's quite a complicated topic, so if you have some additional question to me, please ask after this talk or send us an email. And now I'm giving the microphone back to Vigit, who's going to talk about licensing.
Yes, thank you very much. If you please. Okay, so we addressed this part, the framework part, when we have requesters, providers on the platform, but we left out our poor software developers, and we really need them in our solution. And Golem, this single part is one of the most important parts in this project, so we really take care of how to integrate software developers and proprietary software into the Golem. So, right now, we start modestly. We just would like to allow software developers to easily integrate software licensing solutions into our framework, so that it's very easy for them, and so that their existing architecture doesn't have to be changed at all. So this is the prerequisite. We need to address those two things, but to integrate it with Golem, we have to prepare a bit more. So first off, we need API for existing solutions for software providers, so that their frameworks can contact and interact with Golem network. And at the same time, we need to enhance Golem protocol to interact with those special nodes. And this may be license servers or license infrastructure, whatever it is. By the way, we're going to announce announce a Medium post about this protocol enhancement, and then provide you a document with detailed protocol specifications so that you can evaluate it yourself. And additionally, we would like to provide some logic for those servers. It's optional, but it should allow those software developers to better integrate with the network and provide their software in a way that makes it more reliable and maybe not faster, but more trustworthy, which is very, very important. Still, it applies only to the solutions that exist, which are mostly centralized. So we have one more important step ahead of us, and it's decentralizing the beast. So, as far as I know, no one has done that yet. We have at least one good idea how to approach this problem. We're going to try to implement it, provide you a document on that, and our estimates on threats and problems, and, well, the environment which should be constructed for this to work, and the parameters which it should hold to work. For example, the probability that a part of network can. And once we've done that, we need to prepare a process for software developers to integrate their solutions, centralized ones, with this framework, which we hopefully are going to implement in a way that is very, very easy for them to integrate and seamless for users to use. And I think that's it right now. If you have any questions, you can write emails or you can ask us right now. Thank you very much.
Yes, and definitely, please do ask questions. This is a Q&A session, so this is the time for this interaction. I can pass you the microphone, please. Yes. And if you could give us your name.
So, yeah, my name is Lorenzo. And, okay, I wasn't there for the first part, so I might ask something you have already said, hopefully not. My question is, so as far as I understand, jobs in Golem, let's say, I don't know if that's the right term, but something that I want the network to perform for me, they are, in a way, public, right? It's not possible that I can, for example, like, give a task to the network to render something without the network or the people who perform the work to have access to it. Is that the case?
At this point, you cannot, because, well, you can transfer the data in an encrypted way. But so no one on the way can see your data, but at some point you have to decrypt it and render it. So the endpoint is going to see your scene, for example, textures and whatever you have there. Yes.
Okay, any more questions? Someone has any additional questions? No, so, okay, so that's thank you very much, guys.
Okay.
It was an interrupted, indeed, presentation, but thank you for doing it, and thank you for your patience as well. And this is the time, if I could, Philip, if I could.
Thank you.
Thank you.
YouTube is saying the sound is great now.
Oh, really? Yeah, so give a round of applause to the YouTube, please, right now. Yeah. Thank you. The sound is perfect. The vision is perfect. First speech was perfect, and there is going to be a next one where Golem and Streamer overlaps. That's the title for Henry Pichela's next speech. Henry is Streamer's CEO and founder. So, Henry, the floor is already yours, so just take the microphone.
Thank you. Sure. Okay, hi guys. My name is Henry. I'm founder and CEO at Streamer. Thanks to our friends at Golem for having us here, and thank you all for coming here. And hi, Mom, wherever you are. Right. Okay, so here's what's going to happen today. I'm going to explain to you what Streamer is, briefly. And then I'm going to tell you the story of how we came to collaborate with Golem and why, and where the kind of complementary technologies meet and what they could do together, and where the overlap is, which gives us synergies for R&D. So let's get started. So Streamer aims to tokenize the value in real-time data. For example, let's take self-driving car. So to provide the best user experience for the passenger, it constantly needs data from other machines, such as traffic congestion information, electricity prices on nearby charging stations, it's an electric car, of course, weather forecasts, and so on. So Streamer provides a single interface for receiving real-time data and paying for it using a cryptographic token called Datacoin, which lives on the Ethereum blockchain. So basically, this makes data streams tradable by both people and machines. So the car can go, fetch the data it needs and subscribe to it and pay for it. Now, in turn, the car can sell the data it produces, such as traffic information for other cars, road condition measurements to smart cities, passenger blood sugar level to nearby advertisers or whatever. So a data stream economy is born. Streamer is implemented as a decentralized peer-to-peer network. A data source can connect to any node in the network, publish a new data point, and it instantly gets delivered to valid subscribers. The streamer network scales horizontally up to billions of data points per second, thanks to a clever sharding scheme. The network connects to an underlying blockchain for security-critical operations, such as value transfers and access control. Now, I'd like to make a special note here. So, Streamer is designed to operate within the limits of current-day blockchain scalability, right? So but certainly we could do better things with more scalability in the network. We could have more fine-grained control over the operation of the network and the payments, which is why I'm super interested today to hear the talk by Joseph, Thomas, and Vansa about Plasma. That's certainly something that we could use to make Streamer even better. Anyway, decentralization is achieved by allowing anyone to run a node in the network and earn tokens in exchange for bandwidth that they provide to the network. So effectively, the network is run by its users instead of giant corporations, which means you own, control, and monetize the data that you produce. Decentralization also makes the network more robust against attacks and node failures. In addition to the scalable messaging infrastructure, we are also building two applications. The marketplace will allow the data producers and data consumers to find each other, right? So it's kind of like an app store for data streams. And then there's the Streamer engine. So raw data is sometimes not useful by itself, right? It might need computation. For example, combining with other data streams, filtering, aggregating, visualizing, connecting it to blockchains, connecting it to legacy systems or whatever. So this is why we made the Streamer engine. So it ingests data streams from the network and produces some kind of output. And it has a user interface called the editor, which is based on visual programming. So it looks like this. So it allows you to build data processing systems using a visual paradigm and seamlessly combine off-chain analytics and computations with, for example, on-chain smart contracts. It's live, it's up and running. You can go and sign up and try it out. Anyway, so what does this have to do with Golem? Now, I mentioned the word computation, and I told you about the engine, right? So from the start, we knew quite clearly how to build the network, how to decentralize the network, how to build a decentralized marketplace, but how do we decentralize the computation? Now, if you know what Golem does, they decentralize the computation, right? So we knew that currently they're working on the 3D rendering case, but in their roadmap, they're talking about microservices, long-running processes, and supporting a much broader range of applications that can be run on the Golem platform. So we approached them, and this was the initial idea, to have the Streamer engine running inside the Golem container. So now it's not quite trivial to open network access for this kind of container, since it makes it opens a vulnerability, or it can be used for DDoSing or whatever abuse. So one idea there is to have a gateway, a Streamer client or a Streamer access point, which would have a privilege to open a connection to the streamer network and that way provide a safe path for the engine to receive and transmit data. Now, the first realization here is why does it need to be the streamer engine, right? It could be any application running in there and function in the exact same way. Receiving data from the streamer network, doing something with the data, producing output. Now, the second realization here is that why does the streamer client need to be the only service layer available in there? I mean, you could have a whole bunch, a toolkit of decentralized services available for your application in there. You could have access to Ethereum, you could have some access to a decentralized database or whatever in there. So this kind of starts to highlight a path for a decentralized service stack for creating applications. Now, today, developers create applications and leverage hosted cloud services to make their job easier. You got virtual machines, you got hosted file storage, you have real-time data pipelines that are centralized, you have analytics, you have microservice engines, you have hosted databases, and so on. Now, here's my prediction. I think each of these layers will be replaced by decentralized counterparts, right? So Golem will steal business from the cloud virtual machine workloads. IPFS and Swarm will start replacing the centralized cloud file storage stuff. Streamer will replace the real-time analytics pipelines and data delivery pipelines available in the cloud. Now, Ethereum and other blockchains, clearly, there's something completely new, right? So there's no cloud counterpart to them, but instead, the blockchain actually enables us to decentralize the other layers in the cloud thanks to its uncheatable state transitions. Okay, so in addition to the kind of complementary vision that we can work towards, there's a lot of kind of grassroots level R&D cooperation that we can do. Both projects are thinking about similar problems. For example, both are building their own peer-to-peer network, so we can collaborate on that. Both are thinking about how to assign responsibilities to nodes in the network. The Golem system distributes tasks to nodes. We assign them responsibilities for a certain partition of the data stream. Both are thinking about how to validate the results of computation. Both are figuring out a reputation mechanism for nodes or providers in the network. And also to bring it a little bit more concrete, we're kind of toying around with a few of proof of concept applications out there, not meant to become products by no means, but rather guide the development of both platforms. So for example, we have the favorite of Grzegorz there, the decentralized brain, which is a massive spiking neural network running on thousands of nodes performing computations where the neurons would run in the Golem container and the kind of connections between those neurons would be on the streamer network. Another proof of concept application idea is to try to replicate, for example, the functionality and usability of Uber. If we can build a decentralized Uber with the same user experience, I mean, Uber is the ride company that doesn't own any cars, but can we build a ride company that is there, well, where there is no company, right? So let's take everything out and leave just the service. Now, the methods in which we can collaborate and are collaborating is, for example, code sharing, sharing of research results, arranging workshops, hackathons, developer exchange. One of our guys going. And of course, engaging the community to think about these things. For example, that's what we're doing right now. So we make your streams come true. Thank you very much. So I'd be glad to have any questions
Yes, the
from the audience.
questions time. Please, yes.
Hi, I'm not sure you mentioned something like that, but how do you anonymize the source data?
How do we anonymize the data source? Okay, that's an interesting question. So the network is based on the idea of signing each data point. So basically, we want to know the source of each data because then we can trust that data. So it doesn't take any opinion on what the data content is, right? So you can publish data in there. You don't have to tell who you are. So the identities are, for example, Ethereum identities, and you don't need to bind that to a real-world identity unless you want to, right? So, for example, on the data marketplace, you could have two sellers selling, for example, stock market data fees or whatever, and one of them. So, if as a customer, how do you pick? You know, which am I gonna buy, right? But if the other one identifies them as NASDAQ, you're bound to trust them more. So in that case, identity brings more trust into the system, but you can always remain completely anonymous if you want to. But it's important to be able to prove that a certain data point comes from a certain anonymous identity on the network, which can be accomplished by signing.
Okay, we have time for 2 more questions, please.
Okay, my name's Andy. I spoke to somebody at Tesla the other day who told me that the cars are driving around gathering data all the time. At the moment, where I assume that data is going to a centralized location, and you gave the example of a car. Now, if Tesla were to switch over to a decentralized system, why would they do that? Like, do you expect them to? What would be the benefits of them to do that? And is that really an application for what you're building?
Yeah, I think so. If you think of how organizations today are thinking about data, all of them are collecting data, but they're kind of keeping the cards close to their bodies. You know, they're not sharing. They're barely using that data internally. Probably not the case with Tesla because they're smart. But most organizations collect data and do nothing with that data. So the data is not valuable to the organization itself, nor is it valuable to anybody else, right? So why would Tesla share the data? Well, they can profit out of it. If the profit is larger than any harm that sharing the data does, then it's like a positive expected outcome from that. Of course, companies might not want to share data that can help their competitors, but there's got to be a price tag for that. So if Tesla were to share that data, like $1 million per day or something, and expect to get 10 customers for that, maybe it's peanuts for Tesla, but who knows? I mean, they might. So it's all about the market economics and what value is in the data for the company itself versus releasing that data. And I think this kind of use cases can emerge. Think about if you had, well, let's take an example of like personal measurement. Would you wear a smartwatch which kind of earns you €5 per day or something? It brings new opportunities to business models to be able to monetize on the real-time data.
Okay.
Hi, I'm Chris Hobcroft. I'm working on a project called LivePeer, based out of New York, which is a live video streaming platform. Is there collaboration potential here, do you think? It's a sub-case of live streaming. Could your platform
possible.
take
It's
live
possible.
streaming video?
Yeah. We're concentrating, well, okay. Let's take the kind of technical aspect first. So we don't define the payload of what those events can contain. So it can be binary, it can be anything. But in designing the network, the technical choices we're making are always guided by the idea of the use case that it's some kind of machine data, like sensor measurements or trades coming in from an exchange or something. So it might be possible to do video streaming on a streamer. I wouldn't count that out, but it's possible that we might also have to make some choices along the way that will make it less optimal for that exact use case versus having those, I don't know, IoT measurements going on in there. Yeah. We could try what it would mean. Yeah, very cool.
All right, Henry Pihkala, thank you very much.
Okay. Thank you.
CEO and founder of Streamer. And now I'd like to give the floor to Joanna Rutkowska. She's Invisible Things Labs CEO and founder, Cubes OS founder, and an architect, right? Founder and architect. So reasonably secure computing in the decentralized world and operating system architect's perspective.
Thank you very much. So I come from a different world than most of you. I'm a system level security researcher. I spent several years researching technologies like operating systems, hypervisors, Intel hardware technologies like virtualization technology and other technologies. So, and I have kind of a different perspective on this all. I'm not gonna be talking about networks, network security. How I'm gonna look at these problems through my field. So I just need a slide changer.
There it is.
Okay, thank you. So reasonably secure computing in the decentralized world is the topic of this short presentation. So in the 90s, we all heard this buzzword, the network is the computer, right? And just the problem is how to make this global computer secure. And before we move on, I want to just clarify some of the vocabulary. So with adjective secure, there is something like trusted and trustworthy, and occasionally people confuse them and think that all of them are synonyms, which is not really the case. So first is the trusted. Usually we don't like when things are trusted, because when we say that something is trusted third party or trusted computing base, what this really means is that a compromise or a fault of this component really means the compromise of everything, So we don't like when things are trusted. We want to minimize the amount of trusted parts in a system or in a network. To attack, but secure does not necessarily mean that this is good for the user, because, for example, a backdoor might be secure, meaning that it's quite difficult to hijack it by a different attacker, for example. And then finally we have trustworthy, which is something that is secure and good for the user, whatever really good means in this context. We cannot really say what good is objectively, so that will be always contextual. Okay, so here we have this decentralized network computer, and these blue boxes are our applications, processes, or payloads, and we have a user. Okay, so a user has their processes or applications running somewhere in the cloud. This is the vision we have. This is what, for example, Golem is trying to do. Now we have at least again, from my perspective as a system level security person, there are at least 3 challenges. And challenge number 1 is how to make sure that these blue boxes are actually protected against whoever owns the hardware on which they run. Okay? So if I want to sell my computing power to the Golem network, how do users who will be using my donated hardware, my hardware is not malicious, or I'm not malicious, and I want, for example, I will not spy on them, or maybe I will change their programs that run there to do something else. So we have problem of confidentiality and integrity. And this problem, of course, should not be confused with a complementary problem, which is how to protect the host, so computers of people who donate computing resources to the network. Because this problem is actually much more widely researched, and we as an industry have been trying to solve this problem for at least a decade. All these data centers, all the virtual machines that run in these data centers, they are all concerned that customers do not escape from VMs, right? So this is kind of an orthogonal, complementary problem. However, the first problem is the new kind of problem. Right now, if we go and rent a VM in Amazon or somewhere else, we really need to trust Amazon, which means really need to trust their IT personnel. Because the admins can always do anything they want. And obviously, if we now move to something like Golem, which is totally decentralized, we really don't know the people or the companies who manage the hardware on which our payloads are going to be run. We absolutely need some assurance how to eliminate these vectors, right? So that's challenge number 1. Challenge number 2, which I only briefly will mention today, is that, okay, so we have this computer. Let's say our blue boxes are really protected from these people outside. Now, at the end of the day, we access our data through some terminal. This may be a laptop running Windows, maybe a phone running Android or iOS, or maybe something else. Now, the problem is that we can have the most secure network, secure protocols, whatever. However, if our terminal is compromised, then it's all lost from the security point of view, at least, because a compromised terminal can always see all our secret data, because at the end of the day, they always need to be decrypted before they are presented in front of our eyes, right? So if there is a malware on a laptop and the malware has infected a graphics stack, then of course the malware will see all the secrets. So that's a challenge, how to make these terminals actually trustworthy. Some of you might say, okay, but these are just thin terminals. There are no apps running there, so that should be easy to make them secure, right? But that's not quite true. They still have networking stacks. They have USB stacks, because maybe you want to download our slides that we prepared on Google Docs, like some a friend or whatever. They have networking services running, and there are other attacks open on these devices. At the end of the day, producing such a device to be trustworthy, secure and trustworthy is quite of a challenge. That was challenge number 2. And finally, challenge number 3 is that when I showed you the original picture a few minutes ago, all the boxes were blue. And I somehow tend to use colors to signalize the level of trustworthiness or security of these components. But in fact, they are not all blue. In fact, they have different colors, so they have different levels of trust. Because some of them might be some maybe games, other might be some Google Docs-like applications where we prepare our sensitive work documents. Yet another ones might be email applications, etc. This is all one computer. So the user has a computer, which means there is a large interactions between all these components. Just like today on our Windows or Macs or whatever other devices we have, there's a large interactions between apps. You can exchange clipboard between them, we can send files from one to another, etc., etc. Every such interaction is an attack surface. And so the problem is that if you want to give users something like a computer in the cloud, still we need to solve the problem how to actually make this computer secure. Several years ago, when VDI, Virtual Desktop Infrastructure, appeared on the market, people were really excited. They thought that it was kind of similar, except that we also had Thin Terminal, and then we had all the computing done in a data center. So people were really excited that this will change the security game, because now, for example, Windows will run in the data center. However, the problem with this is that the same, for example, Windows operating system, when run in the cloud, is not going to be suddenly more secure just because it's been running in the cloud. Still, if there is some email application that we start there, this email application will get an email with an attachment. The attachment will be a PDF file, and the PDF file will try to exploit some bug in a PDF Acrobat reader, whatever. This will again happen in the data center. So here is again the same situation, except that we have many data centers. And here we come to KubesOS, which is the project that we've been working for almost 8 years now. Right now, KubesOS is focused on to be a desktop operating system running on laptops. So it has absolutely nothing to do with decentralization and cryptocurrencies. What it does, however, and this is what I'm going to argue, translates one-to-one to what Golem wants to do. So first, what it does currently. Qubes does two things. First of all, it compartmentalizes your desktop computing. So you can define multiple partitions or domains, for example, personal, work, accounting, project X, anonymous web browsing, whatever. It's not enforced what the partitions are. Every user, every company can define by themselves. And there are, of course, tools, how to automate it, etc., etc. But this is only half of what we do, or even less than a half, maybe 20% of the effort how to do that. So right now we actually make use of the Zen hypervisor to create such compartments, which are really virtual machines. But most of the effort goes into what we do on top of these compartmentalized compartments, which is the careful integration. Because again, a desktop system is one system. There's one user, one mind, so there must be one system. So all these 15 compartments must be somehow integrated together to present a consistent user system. So this integration of top of compartments is really the main point of most of our efforts. And a trivial example, we have a work email VM where we can have, say, Thunderbird or Microsoft Outlook email client. We get this email with an attachment, PDF attachment. So instead of opening in the same VM, this could be VM or container, whatever, we use a special service that Qubes provides, and the file is seamlessly being transferred to a new newly created VM, disposable VM as we call it. Now in this newly created VM, a PDF viewer, which might be large and buggy and complex, is started, opens the file, presents to the user. When the user is done with it, it closes the PDF viewer, the disposable VM is destroyed. And this all is happening seamless to the user. Now, this looks really simple, but in computer security, usually the devil is in the details, and this is exactly what happens here. Securely transfer file from one compartment to another if they mutually don't trust each other. Again, exposing, for example, network file sharing between VMs is not an option because this is too large an attack surface. So we have special ways to solve that. Another big question is how to virtualize Gui. So we have one VM and then another VM where the PDF viewer runs. How to securely capture what this VM displays and put it on the one common desktop without compromising security.
No, it's fine.
That's fine?
Yeah.
Okay. So, problems like these.
Okay.
Does it work better? Yes. Yep. Okay. And there are many more problems like this, but this is not time for discussing Kubes architecture today. I just want to stress one thing, that we can see Kubes architecture on 3 levels. First level is this isolation layer, and as I said, currently we use Xen hypervisor. We might also have used or might use in the future KVM or something else. We might use maybe Amazon Cloud VMs. We don't, but we might. Or maybe Golem containers. The idea, at least for a few years now, we have rewritten our stack in a way that this lowest layer should be exchangeable. Because really, the core of the cubes is this green layer here, which we call Kubes core stack, and which really implements, for example, the infrastructure for the inter-VM communication that we believe is significantly more secure than what we could have achieved with standard technologies, GUI virtualization, etc. And then finally, we have Kube services and applications that are built on top of these. And these are services like, for example, handling this request to open file in a different VM, or to convert PDF from untrusted to trusted, or to use GPG backend, and many, many others. Again, it's not a good time to go into the details. The point is that by exchanging this upper layer from simple Xen on a x86 laptop to something like Golem, which is a computer in the cloud, the centralized computer in the cloud, everything down should remain the same and essentially run out of the box without any modification. So it looks to me that this might be a good application for Golem. So Golem becoming a platform for cubes. And that sounds actually quite exciting. But before that happens, we should also solve the problem number one, the challenge number one that I mentioned at the beginning, which again is how to make sure that our payloads running on untrusted hardware can be secured from the untrusted hardware. This is really absolutely required here, because obviously if we are talking about running my computer, moving my computer, my Mac or my Windows to the cloud, it's really required that confidentiality and integrity be provided for all the payloads. it's not enough. This can't be solved with any kind of statistical network level security. This must be solved on CPU level security. And as a matter of fact, one of the first areas of our cooperation is to actually try to approach this problem. So that's the long-term vision of cubes and Golem. And if you have any questions, it's a good time now.
But reasonably secure computing in the decentralized world. I'm sure you have questions to Joanna. Yes, please.
That's a question which is hard to answer because it would depend on how specifically Golem would be implemented. From the Cube's OS perspective, in this vision that I presented, we expect that Golem will expose us some kind of API similar to, say, OpenStack or API used for EC2 management or any other virtualization system. Now, will this API allow and will the infrastructure allow for anonymous use of computing power? That's really the question for Golem people, not me. I don't see right now anything in this Cube's part of the architecture that fundamentally would prevent that, okay?
How does a user interface with the operating system?
Through this trusted terminal, that was problem number 2, how to solve, which was, sorry for jumping. That was this red thing here. This is your trusted terminal. Maybe this is your iPhone. Maybe this is your Windows computer with a browser. I don't really recommend that option. Or
It's an app, or it's a browser, or it's a...
Again, it might be an app, but for users who really want more security, that might be a specialized terminal that would also be resistant to, say, evil mate attacks or secure boot bypassing attacks. Or maybe this will be a Cube's laptop because it will have isolated Wi-Fi stack, etc. Again, different kinds of users will settle for different solutions, I imagine.
Hi. You mentioned for a while CPUs, and previously on the Golem presentation there was a mentioning of machine learning. And right now machine learning works really fast. It gets accelerated very well on GPUs. Is it possible to isolate GPUs as well with CubeOS, and maybe even, I don't know if this is even possible right now, tensor processing units? I don't know.
Okay, so that's a very complex question because these are really two questions. First question was, is it possible to securely virtualize GPU, as I understand? The answer is probably yes. Some GPU cards, like Intel GPUs, they do have special hardware provisions for virtualization or multiplexing. We don't have support for that in Cubes yet, but there are some projects, ongoing projects, more like research projects, but they are, for example, supported by Intel, like Zen GT, that try to do that. But even more tricky question is, can we use GPU on untrusted hardware and still protect from this untrusted hardware? This is even more complex question to which I'm not able to answer at this moment.
Okay.
Okay, thank you.
Thank you very much, Joanna. Thank you. And now I'd like to ask you to listen to our summary of what has been said in Henry's speech and Joanna's speech. Grzegorz Borowik is our senior software engineer. So please, Grzegorz, the floor is yours.
Yes, so thank you for introducing me. And I would like to sum up this, guys, what it was said here. So I will deliver here a metaphor what Golem is and how we may understand Golem. So thinking about our cars, we know that they are stuck at the parking lots most of their lifetime. So Golem is to bring computers to the life. And even our cars are in traffic. Usually there are still one guy in a car, it is a driver. So we may imagine that we usually run one program on our computer, but assuming that it requires more computational power, the nicest thing that may happen is to delegate this task to the other computers. So I think it can be only done in a collaboration with these guys as Stream and Joanna. So as Henry said, these technologies are somehow complementary to each other because computations cannot be done without the data, and they know how to deliver this data. And on the top of this collaboration, there is a Joanna. She is going to make this system safe and secure. And our vision is that user in the future will take this system and will have to aggregate the data and have the problem solved. Thank you.
Thank you. Thank you very much. Yeah, okay. All right, guys, I know we already had a break, and it was quite long. It should be quite shorter, but let's take another one, much shorter, 5-minute break. We're going to continue with our meetup. That concludes this part that's been called Golem, Plans, and Friends. But of course, it doesn't mean that in this other section, in the second section, we are not going to listen to our friends. Yes, we are. Please stay tuned, and please come back to the audience, and we're going to continue with our meetup. Thank you. Yeah. Pokazuj ludzi, pokazuj ludzi. 1, 2. All right, guys, we are ready to continue with our meetup, the second part of it. Okay? Zaczynamy za 30 sekund. Okay, all right. Guys, we are back. You are back. We are back with our live streaming. So the second part of our meetup, the title of it, is The Future of Money and Scalability of dApps. So you already came here. So thank you very much for this. I'd like to present our next speaker. Omize's Go's Managing Director and Thomas Greco, Omize Go's Special Advisor. So your speech is entitled, What Scaling Through Plasma Means for Money, both Fiat and Crypto.
Hello? No, I think that. And then we have a clicker. Okay, so before we start, I was asked to clarify again the relationship between Golem and Omize Go. So we are not collaborating, but however, the relationship is that IMAP is supporting Omize Go, working together to build aspects of the Omize Go network. So with that, I will go into our presentation. So I'm going to give a brief overview of who we are, how we came about, and what problems we're trying to address, and what our products are. And then Thomas will jump in and talk more about the Omize Go network itself. I don't think the clicker works. Oh, it doesn't? No, I don't think so. I'm clicking. Yep, okay. So a brief history about how Omize Go came about. We are a subsidiary of a company called Omize, which is a payment gateway company. So that company was founded in 2013, initially with an office in Bangkok. The motto of Omize is online payments for everyone. And what we quickly realized is that with a payment gateway business, what we were doing is processing credit cards, right? So that's not exactly everyone. So we started looking at different technologies that can, thank you, that can help expand financial inclusion. So in 2015, we founded the Omize Blockchain Lab, which was spending most of their R&D time looking at scalability on a blockchain, because if we wanted to make payments work, we need to be able to do micro payments and microtransaction. One of the things that we did was we funded Ethereum dev grants and became very involved with a couple of different projects like the Raiden network. A lot of that learning was then channeled to develop a product that we think we can commercialize. So in early 2017, we registered the Omize Blockchain Lab into a company called Omize Go. And as you know, we had a crowd sale earlier this year, and now we're moving into implementation of the Omize Go blockchain. It's not working again. So as Julian mentioned earlier, our model is unbank the banked. So what that means to us is disrupting financial systems today, right? financial systems are reliant upon centralized entities, which in Asia becomes a huge problem because there's a lot of population in dispersed areas where infrastructures for financial services don't actually cover. So I'm not sure if you're familiar with the stats, but about 73% of population in Asia do not have access to formal financial services. So we're looking to tackle that by bringing decentralized system into the payment landscape. What we realize is that when we're saying financial inclusion, that's a really big topic, right? So one of the first low-hanging fruit that we identified was tackling the wallet business. So in Asia, wallets have huge potential because, as I mentioned, infrastructure isn't readily accessible for most of the population. So what if you can actually store value in your smartphone, which, by the way, it's 133% coverage in Thailand alone, right? That's more than population. It's kind of crazy. So we see it as a vehicle where people can transact money directly with each other. The problem with wallets in Asia right now, though, is that the adoption's so low because with different brands, you can only use wallets in a silo. So if I was a wallet provider, right, if I was WeChat, or if I was True Money Wallet, which is one of the bigger wallet providers in Thailand, my customers can only use my wallet to pay for certain things where I have business arrangements with. So this silo becomes a problem because you load the money into your wallet and then it just sits there. And if there isn't a lot of acceptance points, then there's no point in using your mobile wallet. Why don't you just use cash, right? So that's the issue that we're looking to tackle. So with our solution, what we're building is two things. One is the Untitled Chapter network, which ultimately is a decentralized exchange. The way that users can interact with this exchange to be able to trade values, send value to each other, and pay for things is through the wallet SDK. So we're making this white label wallet SDK available for free for anyone because we want people to start adopting mobile use for wallets, right, for payments, and be able to easily interact with the decentralized exchange. So when we were researching scalability, one of the main issues, as I mentioned earlier, is the ability to make microtransaction. So this is just, Joseph will go into more detail about Plasma, and Thomas will talk more about the decentralized exchange, but I just wanted to show the comparison, what we took in consideration when we were looking at the different constructs, right? So if you're looking to replace Visa, for example, not that we are, at peak, Visa is processing about 56,000 transactions per second. So we needed to do a lot better than that if we were to take on the entire card network. So right now, the way that Plasma is designed, we're aiming at about 1 million transactions per second. So the different use cases that we see from the business perspective is to be able to use the decentralized exchange for converting anything, any value connected to the internet, whether or not it's your currency, digital currency, game points, loyalty points. People should be able to transact directly with each other and exchange all these different points, right? Also payments. Untitled Go was born out of a payment business. So we're looking to actually bolster both services by using Untitled Go as a rail to support Untitled Payment Gateway. Also, Untitled Payment Gateway can act as a place of acceptance. So we have over 8,000 acceptance points right now in Asia. And so people using wallet on the Untitled Go network can actually have access to pay for services on day one through Untitled acceptance layers. And then now Thomas will jump in and talk more about the network itself.
Hello. So yeah, what is the OMG network? It's Can I stand over here? Yeah, so basically one thing to understand about this project is that there's kind of like two layers, right? There's the network layer, and there's the stuff you do on the network layer. And the stuff you do on the network layer is really interesting to the network layer and its customers and their customers in turn. But the network layer is potentially interesting to everyone. And when I say everyone, I essentially mean everyone in the crypto community and also everyone who wishes to have financial sovereignty and be able to transact their own value. So, the OMG network is a decentralized exchange liquidity provider mechanism, clearinghouse messaging network, and asset-backed blockchain gateway constructed as a public proof-of-stake blockchain. The first project designed to use Plasma, which is the second layer scaling solution for Ethereum, co-authored by Poon and Buterin. And it is essentially a non-federated companion chain to Ethereum, to which it is bonded for economic security. So, some things that make the Omise Go decentralized exchange quite unique is that it is actually a fully on-chain exchange, and yet it is highly performant due to the Plasma architecture. The trading engine is built directly into the heart of a blockchain, the consensus layer. It is cross-chain compatible, but there are no need for middleman blockchains. You don't have to spin up another blockchain in order to connect the Omise Go network to trade between other exchanges, between other blockchains. Instead of doing that, the OMG network, Omise Go network, uses contract bonding or a clearinghouse construction for Bitcoin or Bitcoin-like coins. We think that this actually solves the security versus performance issue by putting all the vital stuff for a decentralized exchange, order book, execution functions, on-chain, but on a specialized chain. And the specialized chain, it's very nice if it has a large value, and so it's more difficult to attack, but regardless, it's backed up by Big Brother, the Ethereum mainnet. And differences with other decentralized exchange efforts or projects? Well, the OMG network, it's new blockchain infrastructure. It doesn't just sit on top of an existing blockchain. Again, the order book matching, commit, and execution, they all happen in the consensus of the OMG network. And it does not require intermediary blockchains for cross-chain trading. Yep, once again, very secure, as secure as Ethereum at the very least. So one thing to understand, and I think that it's worth emphasizing very strongly this point, is that the OMG network, and I like to call it that because it is, yes, Omise Go has taken up the mandate to build this network along with friends who will contribute, but it is actually not owned by Omise Go. It is a completely public, permissionless network. So that means it is owned by nobody, but anybody can help run it. It is, in essence, like Bitcoin or like Ethereum. So maybe a question is, why is a private company building a public network that they will not have some proprietary or advantageous ownership of? And the answer to that is because the long vision. The long vision is that the payments industry has kind of gotten itself into the place that it's at because of the idea that owning a network is a good idea. And of course, until Nakamoto consensus came around, maybe there weren't many opportunities to not do this. But we can see that the problems have been there, and what are the problems? Monopoly and oligopoly of entrenched parties. They end up with these rent extraction situations where they charge more to use than is really necessary. They made and developed and improved in ways that will make them a better user experience because there simply isn't enough incentive for the control of the network. It's resistant to improvements because the improvements that do not improve conditions for the owners. So on the other hand, a decentralized network that is run by its users, which does not charge more than the cost of maintenance, which of course includes the economic incentives built in, is resistant to usury, is resistant to rent extraction, and which can be iterated upon and improved by users. So, whatever the governance mechanism, there actually is one, and it isn't some guys that own it say what everybody else has to do. Omise Go, Omise, I should say, actually recognized that this is a very, very good idea. They got involved with Ethereum in 2015 because there was some potential, and it turned out that the potential was, nothing less than, the Nakamoto innovation itself. So infrastructure that nobody owns, Omise actually wants to use it themselves, and there just isn't anybody else who is building it right now. So it's really a win-win-win situation. You win, your counterparty wins, and the passive environment, actors who are not directly involved in the transaction also wins. You can say that's the community, because this network ends up being something that anybody can use for transacting any value that is quite easy to plug into it. And we think that there should be quite a lot of usage. And one of the nice things about building something that nobody in general can object to is that nobody blocks the way and everybody comes with you. It's a very mutually supportive kind of environment that you get. So good strategy. And this is actually happening quite soon, but you don't take any action. You don't give your private key to anyone. A lot of people have lost a lot of money because they didn't think carefully, or maybe they were just too eager. At block 3988888, which was on 7th of July, almost 2 months ago, which was shortly after the OMG sale closed. Per the agreement written in the sale document for the OMG sale, 5% of the total OMG supply was allocated to be airdropped to the entire Ethereum network, which is filtering out like dust addresses, and it's a good compromise. Any account that at block height 3988888 had greater than 0.1 ETH, so not equal or greater than. So one way over is greater than. 0.1 ETH will get an airdrop of this 5% in proportion to the amount of ETH they have relative to the entire Ether supply at that block. And this comes out to over 450,000, so close to 500,000 unique addresses on the Ethereum network gets, free OMG. It's maybe like, about $50 million or something. Price goes up and down. So hard to keep up. But that means that every 1 ETH that someone had, they get about that much. 500,000 ETH holders will receive it. Why do this? Very good reason, actually. The OMG network is a proof of stake network, slasher model proof of stake. So it means that you need to have security deposits in order to stake on the network. Solves the nothing at stake problem. And this network security it will depend on the strength of its validator set. Larger is better. So 500,000 validators, pretty good. But yeah. Currently, there are about 40,000 addresses, according to Etherscan, that have OMG. And after the airdrop, we hope that we'll see more than 10 times that end up holding OMG. Yeah, you know, really at Omise, something that I have really observed is that people just like doing things that they feel good about and that work for everyone, and it doesn't compromise like business, and it doesn't compromise how well you sleep at night and how well you get along with other people. I think that by doing things that we can universalize, that we can see, this is good, we're one to do this, we're others to then, because one did it, also do it. It makes the world kind of a nice place. I think that everyone really feels very strongly about the FOSS, or free software, open source ethos. And it's just very good to do things that feel good. It's very difficult to define exactly what good is. You can't know what good is until you've defined good, so it's begging the question, it's circular. Instead of getting into meta-ethics, we just know what feels right, and we kind of check with our peers, this feels right, this is good, okay, we do it.
Thank you, Thomas. Vanza, Thomas, thank you very much. Great interaction. So let's have some more. I'm sure you have some questions. Yes, please.
Thank you. Transferring any kind of value on a global scale, does that bring you guys into any kind of like trouble with regulations like all the time?
Two things. One, it's not our network. Two, the white label open source wallet SDK is customizable. And the SDK is largely for digital wallets that are wallet providers, existing wallet providers, which are already compliant with whatever regulations of the jurisdiction that they're in. And so they will require having digital wallet license or money transmitter license or store of value license. Yeah, basically, the onus is on them to comply. And there's customizability very easily for them, that if they are barred from being able to do certain kinds of transactions in their jurisdiction, then they can offer that service. Somebody else might want to offer that service, but as a company, Omise Go would also comply and not like offer contracting type service to help non-compliant entities set up. But it's all open source.
Where's Omise Go based?
Probably best. You mean where is it registered? Yes, Singapore. So, good balance between open market and very careful control in some ways.
Yes.
So when you go into a shop and there's like the sticker on the till that's got like Visa and MasterCard, is your goal to have Omise Go on that same sticker strip, or are you somewhere in the background? Are you going to be right at the forefront of people using you instead of these services potentially?
Well, so if people really want to use Visa MasterCard, then they should have the freedom to.
Mm-hmm.
And Visa MasterCard plugs in very well because Omise Payments is an acceptance point for things like Visa MasterCard. And so Omise Go, yeah, you can connect to Visa MasterCard quite easily. At the same time, so in Asia, it's actually quite common to have like a QR code. It's like like 3D barcode sticker. And services like Alipay or WeChat Pay, people, buying a bottle of water or a coconut from a street vendor, actually, can just do that scan really quick. And the idea is that if people want to continue to pay with WeChat Pay, then they also should have the freedom to do that. But in theory, example only, WeChat Pay could also plug perfectly into Omise Go.
And the merchant that takes that payment, would they hold that as a cryptocurrency, or would it get converted into something?
No, because the merchant that takes the payment is taking the payment in a fiat currency of some sort. The fiat currency that is being able to be paid in has been issued in the form of a fiat token that is backed by the reserve and the regulatory structure of the jurisdiction that the issuer is in. And essentially, this and Plasma in general is a full reserve model. So one of the things we didn't really touch on is that we think that this is a really good place to keep your money, because typically e-wallet licenses, digital wallet licenses, these are quite different from banking licenses. You cannot just arbitrarily, or actually not even unarbitrarily, you cannot loan out the money that your depositors give. You actually have to keep it, and typically the license is like a central bank. And so what this means is that people can end up using a system like this as a full reserve bank account. But then one that is actually also quite handy. You can do payments directly from it.
So also to add, going back to our initial vision is to improve financial inclusion, right? It's about giving that third or fourth option to users as well. That if they don't want to use Master or Visa card, if they don't want to open a bank account, which in most places you require to hold some sort of balance, that new option.
Yeah, so the idea of financial inclusion sometimes is thought to be, okay, like poor people who don't have a bank account, but actually maybe financial freedom or financial equity, equitability is preferable, because, I mean, when you think about it, there are these financial systems that sometimes users would prefer to use if only they were to know about it, because they want the benefits. They don't necessarily want to, if they're a merchant, possibly have this huge fraud risk, which card authorization networks, just by the very structure of them, they will always favor the user and not the merchant. So yeah, there's these things that you can really cut out of the system. If you think of financial inclusion as being something that is inclusive for everyone, not just people who don't have bank accounts, but what if people who have bank accounts want to use a different financial system? They don't want to use their bank account anymore. This is a way out of that without just becoming another bank. This actually changes the properties of the system.
I was wondering if you could explain what Plasma is for people who don't know.
That's in a brief moment.
All right. So just wait, Lorenzo.
Right? Yes, please, just a second.
Thank you. It's David. Just one more question on the on your token, given that you're about to airdrop it on everyone who has an Ethereum address, which presumably then includes me. And given that you just mentioned that you don't own the network, what does the token actually do? I mean, what type of token is it? What do I get out of the token other than being gifted one?
So it's a proof of stake network. So it's different from like a network that you run hardware, and increasingly so specialized hardware, burning lots of electricity to compete with other people to solve, to guess the answer to a really, really, difficult, computationally difficult math problem. Instead of that, what you can do is you can have this token, and it basically acts as, kind of like a permission or like a license, a key, that you can operate a piece of software that is fairly light and just is involved in transacting, in proposing or in confirming blocks that other people propose. And you need to use this token as a deposit. And this token has to have some sort of value, because the idea is that you need a reason to, everyone needs a reason to believe that everyone else is being honest, right?
Where's the value derived from?
Where's the value of? Where's the value of? Okay. So there's two layers to that question. Ultimately, where is the value of Bitcoin derived from? Right. Ultimately, if we assume that it must be somehow on top, on the top layer of the network, then we can look at what goes on the top layer of the network, and then what goes on the top layer of the network is essentially like Bitcoin without the Bitcoin. It's essentially financial transaction that is currency agnostic. So what this means is that people can issue their own tokens on it, and if you trust that these people's tokens are good for something, because say you trust the governments, or you trust the institutions, or you trust the organizations, then you're willing to accept that token for something or another. And if you trust that the tokens on all these other blockchains that can plug in to the OMG network, if you trust that those tokens are worth something, then that can be traded through this network as well. So essentially, that is the value that's on top. And the OMG token value is just the value that people expect that, staking, you get a reward, and the value is also in the reward from the staked token.
Okay, thank you very much. So it was Banza and Thomas of Untitled Go. And Plasma was already mentioned in their speech, and Plasma was asked for. So here it is, introducing Plasma, Joseph Poon of Lightning Networks. You're the co-author of Lightning Networks and Untitled Go's principal author.
Great, thanks for the introduction, and thanks for Blue Yard for hosting. Thanks for collaboration, advice, technical advice for Untitled Go, and Golem provided great technical feedback as well as technical analysis of the Untitled Go design, and looking forward to possible future collaboration or friendship at the minimum. So I didn't know how technical to make this presentation, so it's going to be a little bit technical. If I go too fast, do ask me to slow down. I've never given this presentation before, so it might be a little bit rough on the edges. I don't know in terms of timing how long it's going to take, so if it goes too long, do give me a heads up. Before we really go into the design of what it is, what Plasma is, I think it's important to understand sort of the motivation behind it, and as well as the technical constraints from a design and philosophical level on what the implications really are. So when you look at how the security is derived from full validation, right? The notion is that you may not trust what the world is telling you, but you can individually compute it, right? Presuming you have secure hardware, secure software, as was talked about earlier with Cubes. Cubes is great. I run Gen 2, but Cubes is really, really good too. I have another partition for that. So what you really want to do is self-validate what's going on in the world, right? That's the narrative of blockchain. So what that implies is that all activity you have to compute and validate. So if you wanted to compute, for example, the entire world's financial activity on a blockchain, that's going to be a lot of activity that's going to be difficult to compute, on a normal PC at home, right? Financial institutions already have large data centers. How do you get a blockchain which requires full validation of some data set? Well, the solution is to not compute the full data set, right? And to minimize the amount of data being computed. And it's more about, minimizing this ground truth, right? What is the smallest point that you can validate in order to, smallest point which doesn't require deep validation of everything that happens in the world, financially or even non-financially, right? And if you ever disagree about this global consensus state, right, it's very simple, right? There's software and code that you run. If there is disagreement, the other person's incorrect. If there isn't full data, though, complexity, right? It becomes like a he said, she said situation, right? Psychologists, tend to call that insanity when you disagree about the state of the world, right? well, at least one person, you know, you really don't know who, right? So, I mean, you know, otherwise you might be gaslighted or something, right? So you don't know who's doing the gaslighting. So there's a problem around state synchronization around all the participants. You need to enforce the current state. And like I said earlier, with global state, it's very easy. Everyone has all the data, right? But what's interesting is that when you want to push state onto other chains, so for example, like channels such as Lightning, withdrawals are actually the most complex part, right? When you put money into this, into some off-chain network or, you know, child chain network, it's this dynamic where, like, okay, you put money into it, you can all talk about what the state is, but the real proof in the pudding is when you move it back, right? When you move it back to ETH, you're like, okay, this is how much I have, I'm taking it out, right? You don't want to screw that part up, and that's actually the most, like, critical part in all of this, right? And in order to make these proofs, data availability is the biggest complexity, right? Because it's saying that, hey, look, I'm taking my money back into Ethereum. Well, is this money actually yours? Well, I think it is, you know, and how do you, and if the other person can't prove that it isn't, then you're in some real big trouble. So Plasma's design is, you know, we're going to talk a lot about this data availability issue and how it tries to resolve that. So when it comes to, like, understanding Plasma, I think understanding Lightning and payment channels is sort of a prerequisite. So on background, like, I'm not going to go over detail on how it works. There's, like, you know, other presentations that really go into it. But the general idea is that, you know, you commit funds into a pool on chain, and then off chain you do some computation or payments between, you know, two parties. And at that point, you know, you can do infinite transactions because there is no global understanding of what's going on. There's only understanding between those two participants that they pre-committed to, but they can net settle the current state, and that's the exit part. That's the most complex. A network of these can do payments across multiple participants. What's interesting about this on a technical level, if you know you look into, like, distributed systems architecture and stuff like that, is that what we're really doing is two-party synchronicity, right? We're saying these two parties fully understand what's going on, right? And in order to move forward, they must come to agreement. Now, what this means is that both parties have the data availability. The rest of the world doesn't have the data available, but it doesn't matter what the rest of the world thinks. As long as these two parties have data availability on what the current state is, which they do in order to move forward, then at that point, if there needs to be a proof that needs to be proven, that needs to be broadcast on the blockchain that everyone must observe, then the other party is able to do that. The general construction is an attestation and then a possible dispute, right? It's similar to the court system where you present your evidence and the other person has the ability to dispute that. Unlike the court system, this is all programmatic, right? So that works very, very well for payments and certain types of computation. I think there's a lot of smart contracts that can be run in this construction, but there's a lot where there's a lot of complexity that may arise if you do that. One example is, you know, the examples that, for example, Golem talked about. And another example is a decentralized exchange. Because what happens is we're talking about multi-party state transitions. So when you have, you know, potentially thousands of people doing one single agreement together, so in a decentralized exchange example, it's order matching, right? In order to do decentralized order matching, you're probably going to have thousands of participants that need to validate what's going on. And in order to do that between two parties off-chain, that creates complexity. You can up that to n parties, but doing n parties requires liveness. So everybody must be online at the same time in order to do validation, and that creates a lot of complexity when it comes to asserting the current state. Additionally, you want to create incentives against halting the system so that if there are economic incentives to, you know, stop trades, for example, or to stop certain types of computation, video rendering, whatever it may be, then there could be complexities around that. Additionally, you know, you may want to be able to scale the ledger itself, the root blockchain ledger. And right now, in order to do channels, you have to have a record of entry in order to lock up these funds. And that can, you know, Plasma is designed to improve upon that as well. So what we discuss with these issues, really the data availability problem permeates all of these issues. And I really want to hammer this home, right? Like, I feel like you probably will not understand a lot of the design constraints of, for example, Plasma or even Lightning to really understand like the motivations and the design principles behind that. You really need to understand that like, in order to make proofs for other people, you must have the data available. And by moving stuff off the root blockchain where not everyone is validating it, the fact is if not everyone is validating some information, then there may be possibility that they may not have that information in the first place, and that's where the complexity arises. So, summary of what Plasma is. Plasma is a construction of blockchains and blockchains, and the state of these child blockchains are committed to the root chain. So for example, with ETH, whenever I say root chain, ETH, Ethereum. And what is actually Plasma? It's actually just a set of smart contracts on the root blockchain. So you can, hypothetically, write it in Solidity, upload it onto Ethereum, and now you have a Plasma chain. Of course, you need software to manage this on the peer-to-peer level, but at its core, the enforcement and the consensus rules of this child blockchain is done in a set of smart contracts. And these smart contracts are operationally fraud proofs. So what happens is similar to Lightning, where someone makes an assertion on an exit, someone else can provide a dispute or behavior that mitigates data unavailability. Additionally, because you're doing constructions of blockchains and blockchains, the computational design requires a rethinking of how you're doing it, because in order to reach scalability, you may have nested chains. And there's a lot of prior research on this, like Golem talked about. Basically, if you're doing these types of constructions, it's a very, very well-researched topic. It's effectively Mapreduce, except we tweak this and add on the notion of committed proofs, committed Merkleized proofs. And when you have committed Merkleized proofs, the reduce step especially, this allows you to dispute any computation that's done. And if a computation is done incorrectly, provided that you have data available, then at that point, you can roll that block back, and then that block can be recomputed, and then the person that computed incorrectly can get penalized. So there's incentives for correct computation, and anyone else observing the network is able to generate those proofs. And this is compatible with other on-chain scaling solutions, such as sharding as well. And more block availability on the root chain improves reliability and performance. So when it comes to design goals of what Plasma really is designed to do, the notion is that one root blockchain is able to encompass all of the world's computation, financial computation, and otherwise, right? Hypothetically, you can run a social network on top of this and enforce its activities and only have less than 100 bytes committed on Ethereum periodically. And this allows you to do potentially millions or billions of state transitions per second in a scalable manner. Because what happens is what you're committing on Ethereum is very, very small. But other people have the data, the people actually running this network. And if this committed data onto Ethereum is incorrect, anyone else can provide proof that this commitment is incorrect, and that block gets rolled back in this child chain, and you can move forward again. Additionally, another design goal is payments and ledger scalability. So I want to be able to hold 1/100th of 1 cent on the blockchain with no other value, right? You can't credibly do that on Ethereum or Bitcoin today. You can't do it on even a lot of the smaller coins, simply because the transaction fees are probably going to be higher than that. So how do you get like the kind of scalability where you could have like billions or even trillions of ledger entries, and provided that your parent chain is non-Byzantine, you're able to hold funds on there, and done better than a multi-sig type construction, right? We talked about like all of these like different elements of Plasma. Let's go into like each individual one on what's going on, right? So Plasma is not any specific application. Initially, you can use it for payments and things like that. But individually, it's just a contract on the blockchain, right, that's submitted onto the blockchain. And you could have a contract that does a decentralized exchange, you have a contract that does a social network, you have a contract that does micropayments, and each of these are only submitting, block hashes periodically onto Ethereum. Very, very small, right? It's only in the event of Byzantine behavior that, proof is provided and it gets rolled back, as well as any exits onto the root chain and exits with data withholding. So, for example, you can run a private blockchain on top of Plasma. You can run a proof of authority system. Many of these are probably going to be proof of stake systems with tokens. But if you're running a private blockchain, then you could hypothetically upload your private blockchain's consensus rules onto Ethereum. You have your own private network that requires permission to run. But ultimately, it's as an individual within a private blockchain, you're willing to have reasonable assurance because it's backed by the security of Ethereum. So this is sort of like the internet-intranet dichotomy, right? So like a lot of people like shitting on like private chains is like pretty easy nowadays. It's like the consensus is it's like pretty stupid, right? But there's a construction because like you don't like, if you have a private chain, it's like, okay, you're still trusting the guy, This allows you to create a private chain construction where you don't trust them, but because it's ultimately backed by an open system, such as Ethereum. This is just bigger so you can see it because the text is small. So when I talked about periodic commitments to the root chain, what are we really talking about, right? So assume there's some contract on the root chain, which is functionally Plasma. They assume that this is a proof of stake network, although it could be a single party proof of authority network. Let's run with the single party proof of authority network because it's easier to conceptualize, right? So assume a single party is generating blocks, right? And this single party, assume they have incentives to like continue generating blocks, but you don't really trust them to do computation correctly because let's say you're Alice, right? You want to hold 1 to ETH and someone's generating blocks, right? Well, that guy can create an invalid state transition and says like, Alice sent all the money to me, I'm going to withdraw the funds now, right? That's a big problem, right? You don't want to allow that. And the way you don't allow that is by saying, okay, every time you generate a new block, you propagate the data, right? We'll go into later what happens when you don't propagate the data, but assume you generate a new block, propagate the data, it's committed onto Ethereum. If that state transition from block 1 to block 2 is invalid, then anyone else can submit a proof, and then that block gets rolled back. I'll show you in a later slide exactly how that happens. But essentially, because you're only submitting very, very small pieces of information, you don't really have to, like, the root chain actually isn't computing it unless there's a dispute, right? You're submitting, like, let's say 100 bytes or so, right? It just gets stored temporarily. After a while, it gets deleted. So Ethereum just goes, okay, I received this 100 bytes. I don't do anything with it. So it just keeps receiving that. And potentially inside this block is like 1 million transactions, right? And that's like, this is like totally feasible with no changes to Ethereum today. So when you reach scale though, data availability is needed to prove the fraud, right? Let's say like we were talking about earlier. Again, this is a bigger picture. So let's say with this, block 3 to block 4, actually what it is that Alice had money here, 1 ETH, right? And this 1 ETH is bonded onto the root chain. So what happens is in this Plasma contract, there's actually Alice's 1 ETH is stored in here in a giant pool. Alice's name isn't attached on the root blockchain. It just says, this Plasma chain has, like, let's say 10 ETH. It doesn't know whose it is, right? Inside this block, Alice knows that she has 1 ETH inside this ledger, but the ledger's not stored here. The ledger's stored here, right? And this, the only thing get broadcast in non-Byzantine states is withdrawals and periodic commitments, like I said earlier. I'm repeating myself because it's like I'm moving very fast, and it may be relevant to go back every so often. So 1 ETH here, let's say the creator of this block says, actually, Alice sent me all her money, and I have all her money now. Oops, right? But Alice never signed off on that. Alice never signed using her private key or anything like that. And the root chain doesn't actually know who owns what at this time, right? Like all they see is just like a hash, right? A signed hash. So what happens is that this is fraudulent behavior, right? And the way you solve that in Lightning is that when fraudulent behavior exists, you prove it, right? But now we're dealing with complex state transitions. So what you need to do is do like a set of fraud proofs. So these smart contracts is a set of compact ways to prove that someone has created a fraudulent block. And it doesn't matter if they do multiple fraudulent blocks, as long as they do something fraudulent in there. The block gets canceled, shut down, and rolled back, right? So this is an example of that. So Alice sees block number 4, and then Alice submits a fraud proof to the root chain. So what this is the Merkle sort of zigzag branch, right, of her transaction. So presume this is a situation where they just delete her funds from the system, right? If this happens, then there's a proof of exclusion that occurs. And the proof of exclusion, what that means is that Alice had her money here, she didn't spend her money here, and her money's not here. So you can provide like multiple Merkle trees on that, and that provides sufficient Merkle proofs. Essentially, you need a state tree of the current state, and then the state tree of the next state, and then a state of transactions which have done a state transition. So you need basically a key value pair of what has transitioned, as well as a state tree of what has of the outputs of all the transactions, basically. And at that point, you order that, and then that works. Yeah, so you need probably at least 3 or 4. So that's well and good, right? You can understand sort of how, if you can prove fraud, then you submit that proof to the root chain. The root chain didn't know anything about the state of these blocks, but there's a sufficient Merkleized proof that you can say, what's done here is wrong, okay? So if you're Alice, you see block 4, you're like, okay, I take this data from block 4, submit a proof, okay. Here's the problem. If you generate block 4, you submit a proof onto the root chain, right? And you don't give anyone the data. This is why data availability is the big problem, and this is what basically all of the prior projects have like stopped on. And the solution is actually pretty simple. Just plan for data availability and allow for exits. Sorry, again? Plan for data availability, unavailability, and allow for exits in the event that happens. So for example, with Lightning, there's a problem of the other party going offline, right? And then you can submit a proof of the current state, and then you exit. Similar with this, you provide a proof of exit, and essentially there's a time delay for anyone else to dispute your exit. If no one else disputes your exit proceeds. So it doesn't actually matter what the contents of this invalid block are. Do you follow? Yeah. Okay, let me try to think of another way to explain it. So you had your money here. Yeah. You have no idea what's in here. You just see a proof that's submitted on here, and you're like, oh, crap. Yeah. Someone's withholding some data, because you can see a proof has been submitted on the root chain, right? So what happens is at that point, you see it submitted on the root chain, you ask around, and no one's giving it to you, right? Yeah. You're just like, I'm getting the heck out. Yeah, okay. So at that point, you have some time value. Let's say it's 1 where you must exit. If you don't exit, there's a possibility that this state transition now becomes valid. Okay. Right? So, I mean, you can tune that parameter to whatever you want. You can set it to a week, a month, it doesn't matter. It's similar to Lightning, where the trade-off is that when you do whatever time parameter you set is also your delay period. So the private blockchain that's running Plasma defines that time? Yeah, as part of the smart contract, when you submit it to the root blockchain, that time that you select is defined in there and pre-agreed upon and cannot be changed. I mean, you can create rules to change it. It's very messy, just make a new chain. So effectively, this allows you to do an exit, right? It's very similar to Lightning, where, if another party seems to be acting Byzantine, the solution's not to try to deal with them, right? The solution's to get the heck out. When someone's a jerk, you leave, right? Again, bigger picture. So there's an issue here where when you do this exit, right, you're submitting to the root chain. If Alice has 1 ETH, it's not that big of a deal, right? When she does her exit, she can pay the transaction fees. But creating an incentive where like the costs of exit are fairly high is not really desirable, right? You want to make this as cheap as possible. You can't create guarantees that it will be cheap, but you can create high degrees of certainty, right? So essentially, what we do instead is create a nested set of plasma chains. And before we were talking about this root contract that allows for off-chain state here. It's minimal effort to say, okay, we also allow this to have off-chain state from here. So you have off-chain state from off-chain state, right? I mean, these are all blockchains, so it's not really off-chain in that way, but it's off the root chain, right? And similarly, you can have something off this first tree depth, right? If the validator of set of this is different from the validator set of this, if there is any type of Byzantine failure, you can say, well, this thing screwed up. At least I can go here. And what's interesting is that their commitments, their block commitments, also flow down. So this means that similarly in ideal circumstances, only 1 hash with signature is submitted here across these many blockchains. And this could be like hundreds or thousands running within here. That's ultimately net settled into a single hash on the root blockchain. And this is how we're talking about achieving millions to billions of transactions per second globally across this network. So here's a concrete example of if this one starts failing and acting Byzantine, what you do is you say, okay, this guy's a jerk. Everyone in here, if you're Alice, let's all just move to here. So they create transactions that say, okay, we're exiting from here and moving to here. And that's all they're doing. And at this point, the transactions here are going to be substantially cheaper than the root chain because it's a proof of stake network or a proof of authority network, and you say, screw it, we're just going to accept everything because this is a Byzantine state and we want to be a good operator, and perhaps there's some token and they want to make sure the token is legit and has some collecting good transaction fees by operating a good network kind of thing. In the worst case, if everything down this line fails, then you always need to go to the root chain, is the construction. So, perhaps you can even go 10 levels deep just to have some reasonable assurance between different parties, and perhaps, some specialized companies can operate one of these. And the fun thing if you were an operator of one of these companies is you don't really have to do much work at all, hypothetically, under certain consensus rules of Plasma, you could just turn your machines off, right? Literally, you just cut your power of everything, and only if one of these chains go down that your customers come calling and they're just like, yo, turn on your machines because we want to do a mass exit off-chain. And that way you can do cheap off-chain exits to coordinate that in order to move everything from one path to another if there is failure. And potentially, if you have reasonable assurance along the chain depth that at least one of these is reliable, you can hold extremely small balances. Right now it's not feasible to hold 0.00001 ETH simply because the transaction fees are above that. But under this, it's feasible to hold very, very small amount. So this is basically thinking of another way of thinking of this is if you're holding large balances or decently sized balances, you have reasonable assurance about going to the root chain under many circumstances, not all, but many. And at that point, maybe you're comfortable holding 1 ETH, 10 ETH, 100 ETH on this. But if you're holding 0.0001, you need all of these to be available, or one of those to be available. So it's sort of a one of n, it's multi-sig construction that's reasonably reliable, is another way of looking at it for small balances. But even with that, there's incentives on the root chain, or not the root chain, the highest level Plasma blockchain. In this case, it's called the first tree depth, in order to continue operation because it assumes a token model, right? So if this has a token in order to generate these proof of stake systems, they're probably going to want to keep the system reliable, because if they start acting faulty, everyone's going to exit the network, and those tokens are going to become less valuable. So the fun part is if you're a user of this system, right, you don't need to observe everything under many circumstances. For some state transitions, you do need full observation, but for an example of payments or something like that, you only need to observe your chain and your parents. So if your funds are in here, you need to observe this chain, and this chain. And that can be pretty compact because, again, with these chains, they're only submitting, Merkle proofs as well. So basically, each new block is, basically not Merkle proofs, block hashes. So they submit block hashes. So there's not much data actually going into this. It's only in Byzantine situations where people are doing mass exits that this is going to have high activity. Otherwise, it's like pretty low volume, and you could probably sync up a week's worth in a matter of seconds. So additionally, because we already have this nested construction, right? Why don't we just throw Mapreduce on there, right? So you can do like complex computation, right? Because this is not just about payments, right? Payments are sort of the foundational layer for creating, financial incentives around computation. But, more than that, I want to be able to literally have, Reddit on the blockchain, for example, right? Where like no one really like owns it or runs it. It's the token holders that continue the operation, and they're incentivized to continue the operation. And I think that would be a pretty fun model for things, right? If you're not familiar with Mapreduce, I think the Golem team went over Mapreduce a little bit. For a word count, the word count example is basically the canonical way to explain Mapreduce. It's not really applicable here because like you sort of need to do all the computation, but why not just run with it? The idea is that for each child chain, you delegate out work. That's the mapping function. And then they do some computation. In this case, you're distributing out books to compute. And then there's some reduce function. And the main difference is that in the reduce step, some of the map steps and all of the reduce steps, you're committing to the computation that you're doing. So for example, if you're running a decentralized exchange or doing Reddit on the blockchain, you need to be able to commit all your state transitions. So for example, in this case, it's trades, or in that case, submission of data, right? So here's the Mapreduce example. In this case, assume this is like a book word count blockchain, which seems silly, but like we're talking about computation on the blockchain, right? And this is like the most simple example. This blockchain, as part of the map function, distributes out work to the child blockchains. So in this case, what you're doing is you're telling these two chains, hey, analyze this book. Hey, analyze this book. And in this chain, they distribute out work in the form of chapters. For example, it's like, hey, read chapter 1, read chapter 2. And what you're telling each one at this child chain is that you're saying, hey, read each individual chapter and count the amount of words where each word has occurred. So for example, the word the occurs, let's say, 150 times. And the word hello occurs, 20 times. And the word world occurs like 10 times or something like that. It returns that to its parent as part of its reduce step and commits to the word count. If it computes the word count incorrectly and there's data availability, then what happens is that anyone else can penalize that computation and it gets invalidated. So you as an individual chain operator has incentive to compute things properly. So they submit their word count to here, they submit their word count to here. This thing combines the two word counts and submits it to here. This thing combines all the word counts, and now it has a word list of all the books that it wants. So now we know out of these sent books, let's say it's from the Library of Congress or something like that, here's like all the words and all the amount of times it comes up. And that comes up in this construction.
Joseph, my back role is to keep the time. So
okay.
we already had some great interaction between you and the audience.
Yeah.
We'd like to have some more.
Okay, cool. I was going to go into like how this applies to decentralized exchange. I'll go into that real quick. Basically, you have a map function in terms of assignment of funds. There's a order that occurs here. All the orders get coalesced into a single order book, similar to how the word counts occur. You reduce that. You take all the children, coalesce that again, reduce, so that you have a single order book of all the orders. And then when the order executes, you do the full cross. And then the assignment is another map step. So you say, okay, you have, let's say, 5 trades that occur here at this price, 5 trades that occur at the same price. And then similarly, they delegate it out, apportion it out, depending on, according to some deterministic rule. And at that point, you have, a full-blown decentralized exchange that can do millions of transactions. Additionally, if you want speed with this, you can localize your trades into here. So if you want, let's say subset 10 seconds for small orders, you could do that there. And if you want, greater amounts, you're willing to do time trade-offs. Okay, so future works, mechanism improvements, recursive ZK snarks helps a lot. Mechanism improvements, you might want to do some more penalties for exits. Currently thinking about that one. Recursive ZK snarks or starks would be helpful. This is not for privacy. A lot of people think this is for privacy. Like that's actually this also like snarks doesn't just give you privacy. It gives you like proofs of computation, which is really fun. So this makes certain exit situations a lot easier to have assurances about. It's not necessary for construction of the system, but it's very helpful. So token incentives and proof-of-stake design. The idea is, you write some code, submit it to the root blockchain, make some tokens. There's incentives to continue operating this child blockchain, Plasma blockchain. And at that point, you now have a system that runs on its own. Like you don't need to like pay AWS or something like that. You just like leave it running. And then like, it just goes. Similar to how like you can't really shut down Bitcoin or Ethereum, right? So to conclude what we're trying to do, the root blockchain is sort of a supreme court of the system. And child trains are sort of the district court. Its parents are sort of like, the appeals court, and the root blockchain, you could say Ethereum is sort of like the supreme court, the sort of ground truth that we're really looking at that we were talking about earlier. So it's really only disputes that are improperly adjudicated which need to be computed. So what we want to do is high volume, low cost, decentralized applications, and then a path forward for sort of showing that Bitcoin scaling and Ethereum scaling is possible. But with Ethereum scaling, you could do like real computation. So for example, putting like Reddit on the blockchain, decentralized exchange, like complex computations that are not just payments or financial activity. We're talking about like really just decentralizing web activity and perhaps like replacing the need for hosted services and making true cloud computing that's very amorphous, right? And potentially allowing for billions of users and transactions and applications. Thank you.
Thank you. And an introduction that was very in-depth. Thank you very much for that, Joseph. And we already have some questions. So yes, please.
Lorenzo?
Yeah, thanks, Joseph. I have one question about the exit scenario and the data availability problem. So assuming that data is not available for me, then I want to do an exit. And I wonder if there's any way to penalize if I want to do an exit, because it's not easy to show or to prove if data was really not available to me, or if I just say it was not available to me. So I should always be able to do and trigger an exit, and would this not be a scenario where I could harm the network by always asking for an exit? And always requiring people to submit the state?
So two parts of this question. So when you do an exit, you do need to submit like a proof, and if you submit an incorrect proof, you get penalized, because when you do an exit, you also need to put up a bond. So that aspect, I think, explains that part. But you also asked the opposite case, where there could be a situation where people may want to force exits onto the root chain. And basically, when you do an exit, ideally you coalesce all the payments into a single exit. So that can be very economically efficient. So the idea is that you pay someone else, and that guy pays someone else on another chain. So for example, on the root chain, they do a payment contingent upon you payment in this child chain. So this person can accumulate a lot of funds, and then they coalesce into a single exit. Assuming they're not Byzantine, that's the optimal situation. It's only when there's halting or data unavailability that there's greater complexity in the design.
Cool. Hey, thanks for the talk. Are there any plans to incentivize third parties to submit fraud proofs?
Yeah, that's actually
because you
so here's there's actually two things to think about with this, right? Yes, there is an incentive to submit fraud proofs because they get slashed, and then the submitter or someone can get rewarded. Here's the problem: if you're a miner, you actually can like take that fraud proofs and say, "Hey, I found it," in like, hey, it's supposed to go to this guy, it's going to go to me now. I don't actually see this as a problem. As long as the fraud gets submitted, I don't care. And you as a user of the system, you shouldn't care either, right? It's just like, yeah, it'd be nice to get $1,000 whenever you see fraud, but like, as long as my money's intact, I don't really care who gets $1,000. It'd be nice if I got it, but the incentive is, my money's still here. That's sufficient incentive, right?
So the question is more like, if only the users, if the users that are concerned with this trade transition have to watch it, you know, and the status quo should be like the system works as expected, then you get to a state where nobody watches it, right? Because I think it's going to work like that. And if nobody is incentivized to like do it in the first place, I see.
So yeah, you can create incentives. There are trade-offs, right? One thing you can do is just have someone watch it on your behalf and just pay them periodically to do that. And that's trivial to do here. And that's sort of what you do on, you know, channel type constructions as well. But to do further incentivization behind that, I don't think it's necessary. But just pay someone else a very, very small amount to watch on your behalf.
For a non-technical person, how does that goes together with OMG?
I think that like this is fundamentally an approach to scaling any type of arbitrary computation on the blockchain that is map reducible. So, you know, decentralized exchange, for example, is map reducible under that context. But this can be applicable for a lot of things, right? It's just, you know, a lot of these things where you're just like, oh, you know, people make, you know, forward contracts on the blockchain. And it's just like, what happens when there's 1 million of these, right? Or it's like, oh, we do this or that on the blockchain, and you're just like, okay, but transaction fees are like $2 right now, right? For this type of complex state transition. How do you make that affordable, right? This is about that.
So that goes for any Ethereum-based
right, this is an approach to that, right? There's going to be multiple approaches, right? But I think this is interesting insofar as that like it's thought about, you know, data availability constraints.
We're now going to switch to this part of
Hey, Marin.
Hey, I'm just wondering about the exit time. So if I'm, let's say I'm 10 levels deep, or in a 10 level deep chain, and then on level 2 there's a problem, can I directly exit in level 2, or do I need to exit in level 10, 9, 8?
No. Yeah, you just exit, you do a mass transition of level 3 and above to exit to some other chain. As long as 3 and above is operational, right? Okay. And then you just coalesce everything and then submit a small proof to level 1 is what you do.
Okay, thank you.
That does require more engineering, and earlier iterations may not do that, though.
We have time for one more question.
Hi. Let's assume we have Alice has her money in one of the blocks, and then Bob is one of the miners, and Alice adds a transaction that Bob doesn't take, and Bob builds a block. How can Alice prove that?
You cannot prove transaction censorship ever, basically. Anywhere, right? Like you just can't do that. So if there is censorship, Alice treats this as halting. So there's basically 2 major attacks: chain halting and like block withholding, right? And functionally they're very, very similar. So if you treat that as chain halting, Alice should get her money out. Because if there's censorship going on, you don't know what else they're going to do later on, so just get out, you know? If someone's a jerk, get out. I mean, that's like the key insight here, right?
Okay, Joseph, thank you very much.
Yeah, thank you.
Thank you. Okay, so this concludes our Berlin, the city of decentralized technology enthusiasts meetup. Thank you very much for this. I know that among you, there are some people who are currently working on making live streaming more reliable, and they want to do it through the decentralized technology. So good luck, guys, really. Golem and our friends are waiting, and I just would like to once again thank you, our friends. I'll start with Joanna Rutkowska. Thank you. Thank you. Let's give the round of applause. of Cubes OS, of course. Henry Piccola of Streamer. Vanza and Thomas of Omise Go. Joseph Poon of Lightning Networks and Cloud Network. And of course, last not but least, our Golem guys, Alexandra and Piotr. Grzegorz Borowik. And Julian Zawistowski, our CEO and founder. Thank you very much. It was a pleasure. And I would like to once again address those guys there. Thank you very much for your patience. Please stay tuned. There'll be another meetups. There'll be another streaming on the meetups. We are going to do it through the decentralized technology for sure. Thank you. Stay tuned to our all means of communications. Twitter, Slack, be there. There's still more to come. Bye-bye. You can wave to them here and here. Thank you. Bye-bye. Thank you.
Wow. You know how to put on the show, man.